To analyze the output resistance of the operational amplifier with and without feedback uh, for voltage series type of feedback. The output resistance is the resistance determined looking back into the feedback amplifier from the output terminal. To find the output resistance with the feedback, that is ROF, two conditions we should follow. The first one, we should reduce the input signal VIN to 0 volts. That is, we should make it short. The second condition, an external predefined voltage source, that is say VO, is applied, which was shown in the figure. Here, V1 is grounded, that is VIN reduces to 0 volts, and at output, a source having the voltage VO is applied. The output resistance ROF is defined as ROF equal to VIN, that is the source input VIN divided by IIN. IO equal to IA plus IB. So since R1 parallel R2 in series with RF is very much greater than RO, so IO equal to IA. That is, see what is the source current, that is IO is split into two equal parts. See, some of the current is IA and the remaining part is IB. So IA will enter into the operational amplifier and IB will enter into the feedback network. Here IA is very much greater than IB. Therefore, the IO is almost all equal to IA. So large amount of current will enter into the operational amplifier. So apply Kirchhoff's voltage law at output loop. VO equal to RO into IA plus A into VID or VD, which is equal to RO into IO, because IA equal to IO plus A into VD. From this, VD equal to V1 minus, generally VD equal to V1 minus V2, which is equal to 0 minus and B into V0, that is the V2 value. So therefore, IO equal to VO minus A into VD divided by RO, and which is equal to VO minus A into B into VO divided by RO. Therefore, the feedback resistance ROF equal to VO divided by IO, which is equal to RO divided by 1 plus AB. That is the output of the operational amplifier, especially resistance. The output resistance of the operational amplifier with the feedback ROF equal to RO divided by 1 plus AB. Here RO is the output resistance of the operational amplifier without feedback, and AB represents operational amplifier loop gain. This equation represents the output resistance of the voltage series feedback amplifier is 1 over 1 plus AB times the output resistance of the operational amplifier without feedback. So here this value is very small because 1 plus AB is very large. So it approaches 0 for an ideal voltage amplifier. The next characteristics of voltage series feedback amplifier: bandwidth with feedback. Now we are going to analyze bandwidth of the operational amplifier with and without feedback. The bandwidth of an operational amplifier is defined as, or any amplifier is defined as, the band of frequencies for which the gain remains constant. The figure shows the open loop gain versus frequency curve of 741 IC operational amplifier. So the curve represents the gain of 2 into 10 power 5 that is a 2 lakhs, the open loop gain, the bandwidth is approximately 5 hertz. On the other hand, the bandwidth is approximately 1 megahertz when the gain is unity. So for an open loop gain of 2 lakhs, the bandwidth is approximately 5 hertz. If the gain is unity, the bandwidth is approximately 1 megahertz. From this curve, we can find. The frequency at which gain equals to 1 is known as unity gain bandwidth. Since gain bandwidth product is a constant, obviously the higher the gain, the smaller the bandwidth. If native feedback is used, gain decreases from capital A to A divided by 1 plus AB. Therefore, the closed loop bandwidth increases by 1 plus AB. The bandwidth with feedback equal to 1 plus AB into bandwidth without feedback. That is FF equal to FO into 1 plus AB. Here FF represents bandwidth of the operational amplifier with feedback and FO represents bandwidth of the operational amplifier without feedback and AB represents open loop gain. It's a loop gain. Next characteristics of the voltage series feedback output offset voltage. See, the offset voltage is some unwanted, that is undesired DC which is present at output of the operational amplifier. So with feedback and without feedback, what about output offset voltage? We are going to analyze output offset voltage with and without feedback, especially voltage series type of feedback. In operational amplifier, even if the input voltage is 0, an output voltage can exist. There are three causes of this unwanted offset voltage at output. Those are input offset voltage, input bias voltage, input offset current. So these are the reasons why some undesired DC will present at output of the operational amplifier. So the figure, that's the circuit diagram is shown. It shows the feedback amplifier with an output offset voltage which is in series with the open loop output AVD. The actual output offset voltage with negative feedback is smaller. Some of the output offset voltage is fed back to the inverting input. After amplification, an output of phase voltage arrives at the output, cancelling most of the original output offset voltage. That is, the output offset voltage without feedback, say V out, and the output offset voltage with feedback equal to V out divided by 1 plus AB. So when loop gain AB is much greater than 1, the closed loop output offset voltage is much smaller than the open loop output offset voltage. So with the feedback, the output offset voltage within the operational amplifier will reduce. The last one, voltage follower. The lowest gain that can be obtained from a non-inverting amplifier with feedback is 1. When the non-inverting amplifier gives unity gain, it is called voltage follower because the output voltage is equal to the input voltage and in phase with the input voltage. In other words, the output voltage follows the input voltage. To obtain voltage follower, R1 is open circuited and RF is a short circuited in a negative feedback amplifier. See the diagram. So this is the actual circuit diagram. Here we should remove R1 The output voltage is exactly equal to input voltage. It means output follows input voltage. VO equal to VIN. So here the actual output voltage equal to open loop gain A into V1 minus V2. V1 equal to VIN, that is the source input, and V2 equal to output voltage. So here the output voltage, entire output voltage is applied as one of the inputs to operational amplifier. So if the open loop gain is equal to 1, so definitely V1 equal to V2, that is V out equal to VIN. The gain of the feedback circuit is 1. Therefore, the closed loop gain AF equal to 1 over B, which